Welcome back everyone. Today we learn about kinematics. Let us start with the differences between distance and displacement. Take a look at a ball bouncing. Now look at these two paths. The blue path represents the distance while the yellow path represents the displacement. Distance refers to the total length covered by an object while displacement refers to distance traveled in a stated direction. This ball is traveling from A to B and to A again. It covers a distance of 2x, but its displacement is 0. Hence, this means displacement is 0 even when it travels a certain distance, so long it ends at the start point. Now, let us talk about speed and velocity. I have object A and object B. Object A moves at a speed of 5 meters per second while object B moves at 5 meters per second, but in the opposite direction. This suggests that the speed of both objects are the same but the velocities are different. Do you know why? Speed is defined as the rate of change of distance moved with respect to time, whereas velocity is the rate of change of displacement with respect to time. Hence velocity is dependent on direction while speed is not. Here are the equations for speed and velocity. Now let us talk about the average speed and instantaneous speed. Average speed is the total distance traveled per unit time, whereas instantaneous speed is the change in distance at a brief point in time. Here are the equations for the both of them. Average velocity is the total displacement traveled per unit time. Here are the equations for average velocity. Alright, now let us go through some questions. Here are two scenarios of the object's motion. Find the average speed and average velocity of the following objects. In order to calculate average speed and average velocity, we have to calculate the total distance and total displacement. In this scenario, the total distance covered by the object is 100 meters under 25 seconds, while its displacement is 0 meters in 25 seconds. Hence, the average speed is total distance divided by the time taken, which is 4 meters per second. Whereas the average velocity, which is the total displacement divided by the total time, which is 0 meters per second. How about this scenario? The distance is easy, just add up the total distance covered, which gives us 100 meters. How about displacement? For displacement we measure the distance between its start and end point. In this case, we can use Pythagoras' theorem to give us 70.7 meters. Then find the average speed and average velocity of 4 meters per second and 2.8 meters per second respectively. Acceleration is the rate of change of velocity with respect to time. Here is the equation of acceleration. Note that it is a change in velocity and not speed. Acceleration occurs when there is either a change in speed, a change in direction, or both. Here are two scenarios. A runner running on a track and a planet orbiting the sun. Does acceleration occur in both scenarios? Yes, both the runner and the planet orbiting has acceleration as they change in direction. A very common constant you might come across is the acceleration due to gravity, which is denoted by the letter g, which is equals to 10 meters per second squared and points towards the center of the Earth. Now let us touch on some questions. A 100m sprinter accelerates from an initial velocity of 0 meters per second to 9.8 meters per second in the first 5 seconds. Thereafter the sprinter maintains his velocity at 9.8 meters per second. What is the average acceleration of the sprinter in the first 5 seconds? What is the acceleration of the sprinter beyond the 5th second? To find the average acceleration of the sprinter, we have to find the total change in velocity and divide it by the time taken by the sprinter. This gives us a total of 1.96 meters per second squared. As for the second part, since the sprinter remains at a constant speed without changing direction, his acceleration is 0. As displacement, velocity and acceleration are vectors, there is a need to pin down the meaning of negative values. For example, if the object moves to the right and we denote its velocity as positive, we need to denote the velocity as negative if the ball changes direction and moves in the opposite direction. Before we move on, here are some important symbols and SI units. Displacement and distance uses meters, velocity and speed uses meter per second, and acceleration uses meter per second squared. In addition, we denote initial and final velocity as u and v respectively. Acceleration and displacement are denoted as a and s respectively. Last but not least, t denotes the time taken. Let us focus on kinematic equations. Recall that average velocity is denoted as total displacement over total time. This is how we represent it as symbols. We have also learnt that acceleration is the change in velocity over time taken. It can be represented as the following equation. This can be further converted into v equals to u plus at. The following two equations are optional to learn. But it shows that both equations are derived from both equation 1 and 2. Here is one equation. In the scenario, time is not given. Next we have the derivation of the next equation in which the final velocity is not stated. An object, which falls from an HDB building, moves at a constant acceleration of 10 meters per second squared. What is the speed of the object after going into freefall for 3 seconds? What is the distance covered by the object in the 3 seconds of freefall? Recall the equation for acceleration? We can substitute the numbers to give us this equation. Hence, the final speed of the object is 10 times 3, which gives us 30 meters per second. Now, in this section, we use the equation of average speed and substitute numbers to give us this equation. This will give us a total distance of 45 meters. Let us cover the following kinematic graphs. Here are 5 graphs that we will be showing you in this section. The following diagram shows a distance-time graph. Note that a distance-time graph can never go below the time axis. Distance is never negative as distance has no direction. The gradient of the graph denotes the speed of the object at a particular instance. The following diagram shows a displacement time graph. Note that a displacement time graph can go below the time axis, as an object going the opposite direction can be denoted as a negative displacement. The gradient of the graph denotes the velocity of the object at a particular instance. Here are the following diagrams for a displacement time graph. It shows an object being stationary, where the graph remains on that point and never moves, causing the gradient and hence its velocity to be 0. An object at constant velocity, suggesting that the gradient of the curve never changes and remains unchanged, giving rise to a straight line. An object with increasing velocity, where the gradient of the curve increases in magnitude with respect to time. And an object with decreasing velocity, whereby the gradient of the curve decrease in magnitude with respect to time. Now let us attempt to draw a distance time and displacement time graph. An object starts off from A at rest and moves to B at a constant velocity of 3 meters in 3 seconds. The object then moves to C in 7 meters for 2 seconds in constant velocity. How can we interpret them as distance time and displacement time graph? Here are the distance and displacement graph as shown. Note that the distance time graph does not go below the time axis as distance can never be negative. Now, let us talk about speed and velocity. This is a speed time graph. The area under the curve represents the distance traveled by the object. However, the gradient can be acceleration if the direction of the object never changes. Here it shows the velocity time graph. The area under the graph represents the change in displacement of the graph. Note that it refers to the change in displacement and not the actual displacement of the object. The gradient of the velocity time graph represents the acceleration of the object. Here are some velocity time graphs which shows the following. An object being stationary or at rest, where the speed and gradient is 0. An object at constant velocity, where the gradient remains 0 over time, suggesting that the graph is a horizontal line. An object in constant deceleration, where the gradient should be negative and constant with respect to time, suggesting that the graph is a downward slope. And an object in constant acceleration, where the gradient should be positive and constant with respect to time, suggesting that the graph is an upward slope. In this graph, there is a point where the gradient is equal to 0. This implies that acceleration is 0 at that point. Lastly, acceleration time graphs. The area under the graph suggests the change in velocity of the graph. Take note that it represents the change and not the exact value of velocity in time. Now let us try to draw some graphs. Here we have an object that decelerates from A to B in 5 seconds. The object then accelerates and reaches A in 5 seconds. How can we interpret this as a speed time, velocity time, and acceleration time graph? Here is the speed and velocity time graph as shown. Remember that we can find the total distance and displacement of the object using the velocity time graph. From this, we calculate the area of the graph. For distance, we add up the areas under the graph. This in turn gives us a total distance of 50 meters. However, for displacement, we have to add up the areas above the axis while subtracting the areas below the time axis. Hence this gives us a displacement of 0. Now we can use this as a way to draw the acceleration time graph. A common mistake students make is to use the speed time graph to draw the acceleration. This is wrong. Take note that acceleration can only be determined by the gradient of the velocity time graph, as both velocity and acceleration are vectors, whereas speed is a scalar. Hence, this should be the acceleration time graph. Let us try some questions on graphs to learn how to interpret the graph. Here is the following displacement time graph of the object. Describe the motion in these two scenarios without calculations. According to the scenario in Part 1, the object is moving at constant velocity away from the origin, whereas the scenario in Part 2 shows that the object moves at a constant velocity towards the origin. This can be seen as the scenarios in Part 1 and 2 are straight lines, and hence the gradient is constant. Determine the displacement traveled by the object at t equals 20 seconds. For this part of the question, the answer is straightforward. All you have to do is to look at the graph. At 20 seconds, it is 300 meters away from the origin. Determine the instantaneous velocity of the object at t equals 10 and 100 seconds. To calculate the velocity, we have to calculate the gradient of the graph at these two times. Hence at 10 seconds, the gradient is 15, hence the velocity is 15 meter per second. As for velocity after 100 seconds, since the change in displacement is 500 m after 30 seconds, the answer is 16.7. However, this method is wrong, as the change of displacement is not 500 but rather negative 500. Hence the answer should be negative 16.7 meters per second. Determine the average velocity of the object for the first 60 seconds of the journey. For this question, take note that we are not calculating the velocity, but rather the average velocity after 60 seconds. Hence we cannot calculate it by using the gradient. We have to find the total displacement and divide it by the time taken. This gives us 6.67 meters per second. Now, let us look at a different graph. Here is the velocity time graph. Take note that although the shape is similar from the previous one is a displacement time graph, while this particular one is a velocity time graph. Do check the quantities before jumping into the question. Find the displacement of the object at t equals 20 seconds. The displacement after 20 seconds can be calculated as the area under the graph. This gives us an answer of 300 meters. Find the acceleration of the object at t equals 10 seconds and 110 seconds. To calculate the acceleration of the graph, we calculate the gradient of the graphs. Since the points on t at 10 and 110 are on straight lines, we can just use the equation of acceleration as it suggests that during the periods of 0 seconds to 20 seconds and 100 seconds and 120 seconds, the acceleration and deceleration would be constant. Hence, this would give us an answer of 1.5 and negative 2.5 meters per second squared. Calculate the average velocity for the first 40 seconds of the journey. To calculate average velocity, we have to find the total displacement of the object, in which we have to calculate the area under the graph. Hence, this should give us an answer of 22.5 meters per second. Circle on the graph and explain briefly the point where the object is at its maximum acceleration. Acceleration is found by using the gradient of the curve. Hence, maximum acceleration occurs when the gradient is at its maximum. Hence, it takes place when time is 70 seconds. Circle on the graph and explain briefly the point where the object is at rest. The definition of at rest means that the object is at 0 meters per second. It may not necessarily mean that an object is stationary, but it means that the velocity of the object is 0, just like when take a U-turn to change from a positive velocity to a negative velocity. Hence, these 2 points would suggest that the object is at rest, as that is where the curve intersects the time axis, suggesting velocity is 0 at these times. Now let us talk about a free-falling object. A common misconception by many students is that acceleration points downwards. However, acceleration points towards the center of the Earth, and is always constant on Earth. Did you know? The acceleration of gravity due to the Moon's gravity is 1.6 meters per second squared. Now, here are some graphs to demonstrate a free-falling object without resistance. Firstly, we have the displacement time graph. Next, the velocity time graph, and lastly, the acceleration time graph. Now, let us compare this with free fall with air resistance, meaning that there is a force acting against the motion of the object falling. As the object falls, velocity increases. An increase in velocity suggests that air resistance will increase. Air resistance will decrease the acceleration of the object, resulting to the net force and acceleration to fall and become 0. When acceleration is 0, object will fall at constant velocity. This constant velocity is known as terminal velocity. Air resistance is proportional to the speed of the object. Higher speed implies more resistance force against the object. Here is a derivation which shows that the acceleration of the object free falling is not 10 but rather less than 10. In fact, the larger the velocity of the object falling, the smaller the acceleration of the object. The acceleration will fall until it approaches 0. This can be understood by Newton's law of motion, but that will be for another chapter under dynamics. On the left, it shows the graphs of an object falling without air resistance. Now let me show you the graphs when an object falling with air resistance. Here we have the displacement time graph, the velocity time graph and the acceleration time graph. Take note that when acceleration is 0, the weight of the object is equal to the air resistance of the object. Hence, the object reaches terminal velocity. That's all for today. Thank you for the effort to learn with me. Stay tuned for more interesting lessons. See you next time. Bye-bye.